All right, the gradient is a vector, so notice I have a vector drawn. It's a vector formed by these partial derivatives. Okay, so the gradient, and again, the notes I handed out to you spells all this out and defines all this. I'm just talking through it so that we can get started on our activity. So the gradient is a vector, so I'm going to put the little vector symbol, made up of the partial derivative of x for this component, the partial derivative of y for that component. Again, if you had a four-dimensional surface, you'd have more terms. So for a three-dimensional surface, okay, so a function that is a three-dimensional surface, the gradient is a two-dimensional vector. You have an x component and a y component. So I have an example of a gradient being shown for a three-dimensional surface. The gradient is a two-dimensional vector. The gradient is always perpendicular to the contours. In this case, they're, contour curves. The gradient is always perpendicular to the contours. Again, this idea stays true whether I have a three-dimensional surface or higher. We can draw pictures for the three-dimensional surface. It also shows the steepest slope from any particular point. Okay, so again, for a three-dimensional function, your vector will be two-dimensional. It's always perpendicular to the contours. So that's what I'm trying to show there, that I tried to draw it perpendicular to the contours. And if you were at this point on your surface, again, I have the contours drawn and not the actual surface, but if I were at that point, the gradient is showing what direction you would go to head in the steepest direction. And the magnitude of your gradient is actually what that slope is. So it shows you the direction of the steepest slope, and then the value of the steepest slope is the magnitude of your gradient. So we have a couple, so you can also think about your tangent plane as having the gradient as, part of its normal vector. That might actually kind of help you see why, because this vector is showing the combination of f sub x and f sub y, and so if from this point you moved straight up or down in the z direction, you can see how you would form a perpendicular to the surface. So this is just the little green arrows in the background. They're showing you the gradient field. So if I move anywhere on the surface, what's the direction of the gradient? So the one that I drew, you can see it's in the direction of what they were showing as the gradient field. This picture up here, gradients can be used for lots of things. So this is a weather map that was showing high and low pressure. Okay, so it's showing high and low pressure. And so, again, this is copied from, somebody in meteorology put this together. They're trying to show the direction of the gradient here. I mean, I started over here and started to, so at this point, the little arrow I have drawn here would be the direction of the gradient. But then by the time I move to this contour, notice perpendicular to the contour, the direction is changed. It's kind of more like the blue line they're showing. And then by the time you move to this contour, it's changed a little bit more. So this is heading up to a high pressure, where this is drawn in red because they're actually showing, like your gradients would actually be going in this direction because you're increasing value if you move this way. If you move the opposite of the gradient, you'd be heading towards this. Instead of heading in the positive steep slope, you'd be heading downhill in the steepest direction. Which sometimes you might be interested in that. Like if you were looking at the contours of the green on a golf course, or one of the greens on a golf course, you want to know the slope that's downhill in the steepest direction. So you actually want the gradients multiplied by -1. Like if you flip your gradients 180 degrees, then you're going to be heading in the downward steepest direction. So that's kind of what they were trying to show here. The true gradients, though, would be pointing in the other direction. These other little pictures that are on here, we're just trying to show the original surface for that one vector. So like here's the surface, then this is your gradient vector from that one point, so you can, or sorry, that's your normal vector. Sorry, here's your gradient vector. Notice the gradient is a two-dimensional vector, so that's why I drew it in a horizontal plane to kind of emphasize that it's a two-dimensional vector. And then this is showing you the surface with the normal vector. And so the normal vector has the same f sub x and f sub y for its x and y components, but then the z is down in the -1 direction. You can see that, yeah, that vector certainly looks perpendicular to the surface at that point. All right, so again, I've kind of worked through, your handout has all these pictures and it kind of talks through things. Aside from tangent planes, there's a couple of lines that people might be interested in. If you look at the picture I have here, the line I have drawn is in the direction of the normal vector of the tangent plane. So it's called the normal line to the plane. It's perpendicular to the plane. And if it's perpendicular to the plane, it means that its direction is the same as the normal vector to the plane. So the normal line to the plane is in the direction of the normal vector to the plane. And how do we find the normal vector to the plane? We use f sub x and we use f sub y and then -1. Okay, so you might want to actually extend the normal vector sometimes to be a whole line. You also might be interested in the tangent line, which would lie in the tangent plane. So if you were interested in a tangent line, it would lie in the tangent plane, and its direction would have to be perpendicular to your normal line. So sometimes people study the tangent line, which is in the tangent plane at the point, along with the normal line, which is perpendicular to the surface at that point. And the tangent line and the normal line are perpendicular to each other. So here would be my tangent line. And it's perpendicular to my normal line. Let's see, I guess one other thing I want to mention before I get you guys working on something. here's a picture of an ellipsoid, and this particular ellipsoid, I mean, I just took a picture out of your book. This particular ellipsoid has formula x squared over 4 plus y squared plus z squared over 9 equals 3. So if you remember from section 12.6, remember in section 12.6 we were learning about quadric surfaces and cylinders. I can tell this is an ellipsoid because all of the variables are squared and of the same sign on the same side of the equal sign. It's not a sphere because this coefficient doesn't match that coefficient, doesn't match this coefficient. So yes, this is an ellipsoid. I have the ellipsoid drawn. I have a tangent plane to that ellipsoid. But this could also be thought of as a four-dimensional function where I set it equal to a specific value of the fourth dimension, and you can then solve for different x, y's, and z's that would actually, so just like, go back to 2 dimensions, let's say my function was x squared plus 4, I could set that equal to 8, and then you could figure out what value of x would give you this function equal to 8. Well, I could do the same thing with any function in any dimension, so you could treat this as a four-dimensional function where you just said, okay, well, I want the function to equal 3. This ellipsoid is the set of all the possible x, y, and z that would make this function equal to 3. So this is the set of all points x, y, z that make f of x, y, z equal, so like some fourth variable w is equal to the function equal 3. Okay, so there's infinitely many points, but they all have to fall on that ellipsoid. If I find a plane tangent to that ellipsoid, then I call it a tangent plane to a level surface. Okay, well, what do I mean by a level surface? Well, when I had a 3D surface and I drew the contours of a 3D surface, we called them level curves because my surface was 3D, my contours are always 1 dimension less. So it would be a 3D functions. R3 has R2 contours, which we call level curves. But if my function is 4D, then its contours are 3-dimensional, and we call them level surfaces. And how you find the tangent plane is very similar to how you find the plane if you have any 3D surface, but because you have technically this four-dimensional function, the z variable has f sub z as its, so you're going to have w would equal f sub x evaluated at whatever point you were interested in, x minus that point plus f of y evaluated at the point you're interested, y minus b plus f sub z evaluated at the point you're interested times z minus c, and then this would be this would be the 3 in the example that I showed, but in general, it's the value of the function at the point you're interested in. Okay, so again, your gradient is serving as part of the normal vector, but you now have a 4th variable, and so -1 is the normal curve for that 4th dimension. So f sub x, f sub y, f sub z are forming the gradient vector in R3, but then your normal vector in R4 would then have the -1. Okay, so it's just trying to point out to you that these concepts extend to higher dimensions, and it's easy enough again for us to talk about 4 dimension and showing pictures of their level surfaces, and their level surfaces can have tangent planes to them. Right, so it's something to kind of get your mind around. I know other classes we've talked about what would the contours of a 4th dimensional function be, and I kind of had you picture balls stacked inside one another, and if the balls are closer together, your 4th dimension function's steeper. If the balls are spread farther apart, it's less steep. So if you want to, you can kind of imagine a bunch of other ellipses inside of each other. And so as you change the value of the function, the size of your ellipse changes. All right, I am going to leave it in terms of that for discussion because I did type up all the important little points on your notes. Instead, I would like you to actually kind of start thinking about the ideas by doing some problems, and so I have a group quiz for you to work on.